Hello everyone, thank you for joining this session where we will discuss the Triton Edge, the all-in-one edge computing camera that Lucid is introducing. I'm Alexis Tessier, Product Marketing Manager at Lucid. This session will view the reason why application designer would like to move toward embedded vision, and we'll discuss the major challenges they will encounter along the way. We'll introduce Lucid answer to those, the all-in-one edge computing Triton Edge camera, and discuss in more detail the benefits of FPGA and what they bring in terms of speed versus power versus flexibility compromise. We'll detail the Xilinx PYNQ framework that we use for the Triton Edge, and we will have a short demonstration of running accelerated OpenCV functions on the Triton Edge FPGA. Just a few words about Lucid Vision Labs. Lucid is a Canadian company with 5 main product families, all of them based on the Ethernet interface. As of today, we have over 90 unique camera models, and all products are designed and manufactured in Canada. Lucid has a global footprint with headquarters in the Vancouver area and satellite offices in Germany, China, Taiwan, and Japan. Looking at the evolution of vision systems, for a long time, vision systems were almost exclusively based on x86 PC-based architecture. And at this time, if you needed faster processing, you had no option unless upgrading your computer, upgrading for faster CPU, more RAM, faster processing speed. We've seen in the last few years a move towards system on chip. System on chip is a device that combines multiple CPU and GPU and other devices in a single chip. By itself, it's not very usable, so most of the time they were built on what we call a system on module, which is a small board that includes some power management and memory controller. And to make it easier to integrate with an interface with other devices, this system on module is quite often used with a carrier board that brings in a lot of interfaces. That's what we've seen as, let's say, the standard development of embedded vision. However, those come with a bit of challenges. The camera gets smaller, they become kind of board-level camera with an embedded interface, a low-level interface like MIPI or LVDS. However, these camera modules need to be integrated to those carrier boards, to this system on chip. So typically an adapter board is designed to provide power to the camera and connect it to the SoC. Depending on the type of cameras and the type of configuration, multiple types of carrier board can be developed either by the camera manufacturer or by the end users. The drawback of this approach is, even though the camera is very small, once you add all these various components, the system size grows bigger. And there are major challenges to solve in terms of processing power, balancing the benefits of edge computing versus the performances. Those embedded computers are not as powerful as a typical Intel or AMD PC-based processor, and the system designer needs to carefully design the system and strategically allocate their resources. And even though it's quite easy to get a proof of concept running or even a small scale prototype, when the application designer wants to move to a full-fledged industrial environment ready device, there are a lot of steps along the way. Once the proof of concept has been validated, the vision engineer must strip away all the unnecessary components from those development kits and build an optimized application that takes up minimal space. This process requires usually a custom carrier board to be designed with just the SoC or the system on module and just what's needed. While an embedded development board can offer time saving for application designer during the POC stage or some kind of prototyping stage, there are still a considerable amount of time and resources and cost that needs to be invested to make it an industrial design. So that's Lucid answer to those issues. It's the Triton Edge, an all-in-one edge computing camera with, at its core, a Xilinx UltraScale MPSoC, pictured here with the new info packaging, which means integrated fan-outs that provide a very small footprint and optimize power consumption with multiple processor functionality and FPGA. So this chip combines ARM processors together with FPGA fabric, and we make this FPGA fabric accessible to the customer. On the front end, we have a Sony-produced CMOS sensor, and this camera is integrated into LUCID factory tough housing based on the Triton series. In detail, what's the Triton Edge? It's an open platform where customers can deploy their unique IP. At its core, again, this MPSoC from Xilinx, and we will use part of the FPGA fabric for running what we call the LUCID virtual camera, which embeds LUCID ISP, so driving the sensor and pre-processing the image, and then connected through this AXI VDMA, which is Xilinx video DMA, we provide access to the customer either through the ARM CPU running Linux or to the FPGA fabric, and we will have over 60% of all the FPGA fabric available for customer IP. The benefits is lower latency and to have edge processing and send only the result to the backend system. So why FPGA processing? FPGA processing is hardware accelerated. It's CPU free in some way. It's not as fast as building a custom ASIC, but it's much cheaper to do it and it's much more flexible. Building an ASIC takes huge amount of investment, and if by any reason the design needs to be updated, it takes again millions. An FPGA on the other end is reconfigurable. It's hardware logic that can be configured on the fly. It's quite different than designing a standard PC-based system in terms of development. However, there are tons of resources available, commercially or open source. Some of them pictured here, like the Xilinx VTS library, Vision library, which is, in a sense, accelerated OpenCV. Accelerated meaning that it's OpenCV function running directly on the FPGA fabric. For the Triton Edge, we leverage Xilinx PYNQ framework. This stands for Python Productivity for Zynq Devices. It's an open source project from Xilinx that provides a Jupyter-based framework with Python API for using the Zynq platform. This enables designers to use the Zynq device without having to use ASIC-style design tool like VHDL. PYNQ framework offers different levels of interaction with the MPSoC platform, suitable for all types of users. On the higher level, on the application side, application designer or let's say industry specialist can get quickly running with the Python interface running through a Jupyter notebook and load and parameterize FPGA overlay. FPGA overlay could be construed as hardware library. Similar to a software library that can be reused for many tasks, an FPGA overlay is a function running on the FPGA, which is kind of a general purpose function that can then be parameterized. Next in the development chain will be software developer, embedded software developer used to C++ development that could leverage this high-level synthesis, HLS in short, to develop custom overlay using C++ and then transcribing them to FPGA configuration using Xilinx VTS development tool. And for hardware engineer used to VHDL development, they have access to the full customization capabilities of the Triton Edge platform, designing their own IP core and FPGA shell from the ground up. When we look at this and we correlate this with the popularity of various development languages for embedded application, this is the IEEE Spectrum ranking for 2021. We see Python is at the top, C++ is well positioned. At the lower end of the spectrum, Verilog and VHDL, which are a lot less people have this capability, but it's also available there. And Lucid will build a network of partners to help you get your application running. Some more detail about the PYNQ framework, calling the Composable overlay. The FPGA resources are finite, and depending on the PXI pipeline, many back and forth processing can happen between various processing steps. The Composable overlay is a way to modify and reconfigure the FPGA on the fly, meaning that parts of the FPGA can keep running while an unused part is reconfigured and can be used in the next processing step. This is using this pipeline on the right-hand side with a combination of software and hardware logic, and it can be used to virtually expand the available FPGA resources. Furthermore, this Triton Edge is not only an AI-capable camera, it's an open platform that can be used for a variety of tasks, but it's of course compatible with AI application and edge-to-cloud application. There are various ways to do this. Xilinx provides the DPU, the Deep Learning Processing Unit. That is a programmable engine for running different type of model, like Caffe or TensorFlow or other type of model. It's cloud enabled with compatibility with AWS IoT or Microsoft Azure. In addition to this, we are working with various partners that have their own AI capabilities that they will build and market for the Triton Edge. So how it works in practice, we have a short demonstration to show today. Using the Triton Edge, in a very simple setup, we have the Triton Edge connected with M12 industrial Ethernet cable through a PoE injector running and connected to a laptop. That's the demo we'll show today. The images acquired by the Sony IMX296 sensor go through the Lucid Virtual Camera ISP, and then they are routed through accelerated function running on the FPGA. We first downscale the resolution from 1.6 megapixel to a bit smaller, and then we run histogram equalization. This will add some high frequency noise, so we then filter it with a median filter and a Gaussian filter, and at last we run fast corner detection on the camera. So first step is connecting the camera. It's power over Ethernet enabled. Camera is connected. We need to wait a few seconds for the camera to acquire its IP address and boot up. So now we are connected to Jupyter. Jupyter is an interactive Python interface that can combine both coding, documentation at the same time. So that's our demo for today. As I explained, the image acquired from the sensor goes through the Lucid Virtual Camera and then routed through VDMA, Video DMA, goes to a resolution conversion stage, then histogram equalization and filtering, and lastly a fast corner detection. Our first step is to connect to our device using the Lucid Arena API. We just acquire a handle to the device, and then we can apply the FPGA overlay. So the configuration for today's demonstration. From this step, we can acquire a device node map. So it's very similar to a GenieCam camera. It's not a GenieCam interface because it's not a GigaVision camera, but the way the API is implemented is quite similar. So we confirm the initial parameters, width and pixel depth and frame rate. And then we can set up the VDMA for acquisition, allocating a few buffers and mapping the DMA for transmission. In today's demonstration, we use ImageZMQ, an open source streaming library that will be used to just transfer the images. And with just a few clicks, we should be able to get the imagery running. So that's the image acquired by the camera and streamed through a standard Ethernet interface. It's not a GigaVision camera. We could see now that image is running. It should be around 30 frames per second. We can tweak a few of the camera nodes. First step is turning off the automatic frame rate control. Same for the exposure. And now we are free to customize some of the camera parameters. So here we edit the exposure time. And running with IPython widget, so an interactive widget that can be used also to control the exposure time. Same thing for the frame rates. Can confirm the frame rate, 34 frames per second. Edit it, 20 frames, it's a bit more jerky. Then, as a benefit of Jupyter, you can come back at any time in the code block, edit it, run the function, run the code block. Here, 5 frames per second, so we see the choppiness of the streaming. And same thing, running IPy widget, so an interactive widget that can be used to control the camera parameters. We'll go over a few more settings like gain. Now we can return the camera to standard mode. At any time, you can add a code block and type in manually your code. So we will just return the automatic exposure to on, which, and we see we made a mistake here. might be true. Yeah, actually no, but we have the output from the API that let us know, okay, the expected parameters continuous. So automated exposure is returned to continuous. Now we can configure the accelerated function. The first step is the resolution conversion. Again, allocating buffer and mapping them through the VDMA. Next one will be to configure the histogram equalization. This will require multiple buffers because we need to get both current frame and previous frame. So this will stretch the histogram across the full dynamic range of the 8-bit pixel encoding. This will add high frequency noise, so we will simply include some filtering, median filter and Gaussian filters. Those have been configured, and we can now set up the fast corner detection. Everything is set up, everything is running in the FPGA. We can just stop the non-resize acquisition, come back and test those various functions. First step is the resolution conversion. So that's the same image that we downscaled and resized. And now the histogram equalization. All of these functions are running 100% of the FPGA with no processing running on the ARM CPU. So the ARM CPU running Linux system can be used for multiple other tasks like protocol, fieldbus, or this type of implementation. And here we have the fast corner detection running. Again, we can create a simple widget and parameterize this FPGA overlay. That's why we call it a hardware library. It's hardware processing, but it's not fixed processing. It can be customized on the fly. And here we see, yeah, the various functions. We can then clean up this demonstration. That's it for this demonstration. So, in summary, Triton Edge, those are the specifications. We're running the Xilinx UltraScale Plus ZU3CG MPSoC. It's a dual-core ARM CPU with associated FPGA logic. We have 2 GB onboard RAM and 16 GB eMMC storage, running Xilinx VTIS, PYNQ, and Ubuntu, based and on the sensor side, the Sony IMX296 sensor, which is a 1.6 megapixel global shutter previous sensor. The Lucid Virtual Camera ISP include all the typical machine vision camera control, exposure, gain, white balancing, color matrix, lookup table, pixel format, region of interest, and GPIO. And for the interface, the camera is equipped with 1 gigabit Ethernet, power over Ethernet, and M12 connector for data transmission, and a M8 GPIO connector, IP67 connector in both cases. We have multiple inputs and outputs, one opto-isolated input and one opto-isolated output, and 2 bidirectional input-output, non-isolated. Dimension 2944 by 45 millimeters, IP67 rating, shock and vibration, and industrial EMC compliant. So in conclusion, the Triton Edge, this all-in-one edge computing camera platform, it's a standalone image acquisition, processing, and GPIO running in a small, enclosed, and ruggedized platform with open configuration where customer can deploy and run their own IP. Leveraging state-of-the-art Xilinx MPSoC and Sony sensor, providing multiple processing capabilities, so locating the processing where it makes sense, part of it accelerated through the FPGA, part of it running on the ARM platform. And in the end, to provide a reduced time to market for embedded vision application designer, not having to deal with industrializing a solution with disparate parts between board level camera, connector, carrier board, and development kits. All of this work has already been done and undertaken by Lucid, and the camera is fully ready to be deployed in an industrial environment. This product will launch with a single unit price of $950 US. We are providing at the moment early sample to solution partner. Again, we are developing a partner network with companies that can have their own intelligence running on the camera and resell it to end users. This camera is also open for end users to deploy and develop their own configuration. Thank you so much. If you have any question, feel free to contact one of the Lucid local office in your area. They are listed there. Thank you and stay lucid.